let's get doing these lectures. Today I want to talk about 29.6, Ampere's law. And solenoids. Okay. To do Ampere's law, we have to do what's called a line integral. And a line integral, it's kind of fancy way of doing an integral rather than just summing things up. But really what you're just trying to do is, let me just say, I like how the book says it's just a fancy sum. But you sum up the effects all along a path. You sum up the effects all along a path. So you've got to have a path to do a line integral. Alright? So a line integral, when you integrate it, you're going to be over some line that you go. It could be a straight line, it could be circle, it could be squirrely and around. But it's going to be around some path. Okay? So when you think of a line integral, let's say we got some B field, we're going to integrate, and that's the field we're going to look at and see that effect of, and we're going to basically see its effect, and we're going to do a dot product over some, so this is our motion or line to integrate over integrate. And this is the B field we will look at for each point on the line. Each point on the line. So, and what we're going to do is, when you do this integral, you sum up the effects of the B field in the direction of the path ds. So you're going to see at each point what this B field, its path did. Now you can think of it a way, if you want to get a non-physics way of looking at it, what you could say is, if I went up and down the rows, and I said, give me all your change now. And I go up and down the rows, and each person would give me all their change now. For some people I would go to is I would go up and down the rows, and that would be my path. Some people give me more money than others. But I would sum up all their change I would collect over everyone as I went. Now if I go up and down the rows, get one path. Say I just went all the way around and just hit the edges of all the rows, the front and back. That would be a different path. I would collect different amounts of money over those paths. So I'm going to see the effect of this B field at each point along my path and then sum up that effect of the B field. If the B field is always in the direction of the path, I'm going to get maximum effect. If the B field is perpendicular to the path, since I'm doing a dot product, it's going to be 0 at that point. And at some points it may be 0, some points it may be parallel. And what we're going to deal with, we're going to try to make it consistent over the whole path. Because that makes our integral a whole lot easier to integrate. And similar to what we did with Gauss's law. Let's do the integral, but know that it's always going to be perpendicular or parallel. So this one, when we do this integral here, this b dot ds, it's either going to be maximized or minimized, being a 0. From a magnitude perspective. Okay? So, what you could say here, if I do this integral over, say, 0 to L, if B is parallel to ds over the whole path, then my integral from 0 to L b dot ds would equal b times L. because you know that would be B, magnitude of B, magnitude of ds, magnitude of S. And evaluate S from 0 to L, and that would equal B times L. Okay. Now, with Ampere's law, we're going to use this to help us out, for that calculation. So let me erase the board. Since I don't have anybody helping me with the video, I'm going to use one board. I couldn't move it around, but that would be stupid. So let's look at Ampere's law, and what we're going to say is, we're going to look at, say we have, here we've got some current. Now, since it's an X, that's the tail of an arrow, so that's into the board, so the current is into the board. Okay. Now, if it goes in, use right-hand rule, go around. So if that's true, then my B field here would look like this. That's my B field. Okay. Now that's what my B field looks like. What if I made my ds in the same direction? Is circular around the wire. Well, if that's true, then this is my ds. It's like that, a circle around the wire. We did that, and that'll give us some R there, some radius. All right. Let's do this integral. Now this we're going to integrate around a loop, so that's why we have this here, B dot ds. They're in the same directions. So it's the magnitude of B times the magnitude of S when we integrate. Well, B is just going to be whatever that magnitude is, and we'll get to that here in a minute. S is going to be all the way around, and how far it is all the way around circumference of the circle? 2 pi times radius. Okay, that makes sense. But we know for a long, straight wire, we know that B, the magnitude of the B vector, is mu naught I over 2 pi r. So let's substitute that in right here. And if we do that, mu naught I over 2 pi r times 2 pi r cancels, so we end up getting that B dot ds for this long straight wire is equal to mu naught I for a long straight wire. And what I will say is that this B dot ds equals mu naught times I, this over that whole path, all the way around, it's got to be a closed path. Now this line integral, we're going to integrate on a line, we got to come back on itself. It's a closed integral. Back onto itself. We started here, and we're going to go back onto itself. We will show, it's barely, you can show that that's valid not just for this geometry, but for magnetism in general. And this is Ampere's law. This is Ampere's law. Notice, it just has to be a closed close the integral. It doesn't matter the shape, it doesn't matter the size of it. It just has to close upon itself. And the key is you integrate the current enclosed by the surface. Excuse me, by the line integral. And I'm going to use here current enclosed, or they have through, enclosed or through that circle that you integrate around. That's the current. And if you use this, you can use this equation to help you find the magnetic field of lots of situations. Lots of situations. Okay. Now, for a solenoid, now the book does example 29.8 is the magnetic field inside a current carrying wire. And that's real similar to the one we did with Gauss's law, which was the electric field inside a current carrying wire. But I want you to look at that, put it in your notes. Put it in your notes. That's a good one. Notice it has the same form. It actually has the same form, actually done very similarly as we did the other one. Now for a solenoid is really just a coil of wire, but it's lots of coils of wire. A solenoid is lots of coils of wire. And if there's lots of them, you want to sum up the B field from each coil. And we sum up the B field from each coil. If we do this, let's look at this. If we was mu naught I enclosed, it would just be one. If we do this, it's not just one of them. It actually becomes however many current, however many loops we have. And I'm going to say N times I. Okay? Now, let's look at what we have here. If that's N times I, what you actually have to do, let's look at a solenoid. So this is like one side of that solenoid. We got the positives up here and the negatives coming in. So this is the coil of wire. This is the coil of wire. So it's coiling around, you got positives. So this is coming from the positive side of the battery going in and just going through like that. Okay. Now, the path you have to integrate here is, and it's in figure 29.31 in your book. If you integrate along this path, what do you notice? So here, you have a B field in this sense. It'll be in this way. The B field's in this direction. Here, the B field equals 0. So and here, B is perpendicular to DS on the sides. So here you got 0 effect on your path. Here you have 0 effect on your path, 0 effect on your path. So really all that matters is here. And so what you have to do is just however long, we'll call that little L, that path is. So if we're going to integrate here, we're really just integrating over this path inside here, because the other three parts of the path, 0, 0, and 0. Perpendicular, it's dot product. Here there's no B field at all. And here it's perpendicular, dot product, 0. So let's just integrate over that. So that's just B times that length. So we get here B times L. And then once you take that, you get that the B field is mu naught, number of turns. N is the number of turns. I didn't define that. Number of turns of wire, number of coils, it's sometimes called. Mu naught N I over L. And sometimes they'll take this and make it a ratio and say that's turns per unit length. And they'll say mu naught little n I, where n is turns per unit length. It's a normalizer. Oops. But this is really all we need to know for that. Okay? Questions? I don't hear any. Maybe you're screaming at me behind your computer, and that's okay. That's okay. I do want to say this about solenoids real quick. And we mentioned this earlier when we actually had real lecture. But the B field for this is going to come back on itself. And what's so interesting, a solenoid inside a solenoid B field is constant in magnitude and direction. So if you want like a capacitor gives an electric field in constant magnitude and direction. If you want a constant magnetic field in magnitude and direction, it has to be inside a solenoid. Inside a solenoid. Hopefully that helps with Ampere's law, section 29.6.